As we all know, light is an electromagnetic form of energy, which means that light will be a part of a electromagnetic spectrum. Light is conceptualized as having a dual nature, that of a particle and that of a wave, and a light wave is the movement of light conceptualized as a wave defined by such properties of light as reflection, refraction, and dispersion. Light wave communication refers to coding of information into the form of light, then transmitting and receiving at the receiving end. Light wave communications can be guided or unguided. So, in guided optical fiber communications, we use optical fibers which are made of glass or plastic. In unguided light wave communications, free space optics is used. It means that light is transmitted through free space. And free space optics is a line of sight communication, while as optical fiber can tolerate some form of bending. Optical fiber communication system can be explained with the help of a block diagram. So here we have the information source. So the information source provides an electrical signal to the transmitter comprising an electrical stage. So here information, it can be audio or video, is converted to electrical signal, then it drives an optical source. The optical source can be an LED or a laser diode, where the electrical signal is converted to optical signal to give modulation of the light wave carrier. The optical source provides electrical to optical conversion, and the transmission medium consists of optical fiber cable which transmits light to the destination. So here we have the optical detector which converts light back into electrical signal. Optical detector can be a photodiode such as a PN junction photodiode, pin photodiode, or avalanche photodiode. It can be even phototransistors or photoconductors. So here, as optical detector, optical signal is converted back to electrical signal. This electrical signal is processed and it reaches the destination. Thus, there is a requirement for electrical interfacing at either end of the optical link, and at present the signal processing is performed electrically. We now have the block diagram of a digital optical fiber link. So initially the input signal from the information source is suitably encoded for optical transmission. The laser drive circuit directly modulates the intensity of the semiconductor laser with the encoded digital signal. Hence, a digital optical signal is launched into the optical fiber cable. The avalanche photodiode detector is followed by a front-end amplifier and equalizer or filter to provide gain as well as linear signal processing and noise bandwidth reduction. The avalanche photodiode converts optical signal back to electrical domain. Finally, you can see that after processing, the signal is decoded and original digital information is retrieved. We now have the block diagram of free space optical communication, wherein a wireless form of connection designed for interconnection of 2 points which have a direct line of sight. So the medium of transmission will be free space or air, and the communication will be line of sight using infrared waves. So the systems operate by taking a standard data or telecommunication signal, converting it into digital format and transmitting it through free space. So here we have the laser diode which converts electrical signal into optical domain. And then we have the transmission optics, again at the receiving end we have the receiving optics, then a detector which converts the transmitted signal from optical domain into electrical domain. It is again amplified and demodulated to receive the data. So the carrier used for transmission of the signal is infrared and is generated by either a high power LED or a laser diode. The basic principles for transmission of signal along the fiber are the same as for transmission through free space. Both involve conversion from electrical to optical domain and vice versa. We will now make a brief comparison between optical fiber communication and free space optics. With regard to cost, there will be high initial investment for optical fiber communications. It involves digging and laying of cables underneath, and for free space optics the cost will be 1/5 of the optical fiber communication link. So again, optical fiber cables are used for long haul links up to 200 kilometers without repeaters, whereas free space optics they have been used for line of sight communications involving distance of 200 to 2000 meters. In security aspects, optical fibers they are shielded. The security aspects are very good. It is very difficult to tap optical fibers, whereas free space optics the security aspect is good. Installation will be difficult for optical fiber communication since it involves digging and laying of cables, and for free space optical communication there is no requirement for digging and laying of cables, so the installation difficulty will be moderate for free space optics. The spectrum license is required for optical fiber communications, whereas for free space optics it is not required. The maintenance requirements are low for optical fiber communications because their cables are laid underground. For free space optics also the maintenance requirements are low. The reliability will be high for optical fiber communications, whereas it will be medium for free space optics. Regarding connectivity, optical fiber cables are used for point-to-point and point-to multi-point short and long haul communications, and free space optics again are used for point-to-point and point-to multi-point short and long haul reach. The deployment time for optical fiber cables will be 4 to 12 months, whereas for free space optics it will be from days to weeks. The provisioning time depends on many factors in the case of optical fiber communications, whereas for free space optics it is immediate. With respect to bandwidth, for single mode fibers it is 100 gigahertz kilometer, and for graded index it is 500 megahertz kilometer at 1300 nanometer wavelengths, and it is 160 megahertz kilometer at 850 nanometer wavelength. So there is a dependency on wavelength. For step index fibers the bandwidth is 20 megahertz kilometers, whereas for free space optics the bandwidth is very high and the available bandwidth can be 20% of carrier frequency. For FSO the bandwidth is of the order of terahertz. A comparison of data rates for optical fiber communication and free space optics. When single mode fibers are used, the data rates can be up to 100 megabits per second for up to 5 kilometers. For multi-mode it is 100 megabits per second for up to 2 kilometers, and it can be of the order of gigabits per second up to 1000 meters, and it can be 10 gigabits per second for up to 550 meters. Whereas for free space optics the data rates are high. It can be as high as 10 gigabits per second, from 2.5 gigabits per second to 10 gigabits per second with wavelength division multiplexing. The choice of free space optics or optical fiber communication depends on the requirement. Both have their own merits and demerits. For the time being we will concentrate on optical fiber communications alone. Thank you for your patient listening.